Hello everyone, and thanks to be part of this TTK tutorial. We will see together a lot of stuff about TTK, but first let me introduce myself. My name is Charles, and I will be assisted during this tutorial by Matthew, that will be available in the chat if you have any questions at any time. The goal here is to be interactive, so at any time if you have any question, please do not hesitate to ask it in the chat, and I will try to answer as soon as possible. Also, please introduce yourself in the chat. It could be a good way to check that everything is working fine. This tutorial is funded by the Vestec project on Kitware. Us at Kitware are providing support for CMake, VTK, ParaView, and we can help you with a variety of KsYiZJ related solution if you need. So now, if everything is set up, let's go deeper into this webinar. Here we will see how we can do some kind of clustering, but instead of using the traditional method, we will try to use the persistence diagram. So this is a topological related descriptor that will track the evolution of features on your data, and we will try to operate the clustering using this persistence diagram. Of course, I will start by introducing what a topological feature is and give you the elder rules which will help us track these topological features in tools which is named the persistence diagram. And once we have seen this, we will see how we can use this tool for clustering. We will see that on an example which will be a simple elevation scalar field because it's more intuitive and more visual, and then I will also show you how we can use this tool on a flat data set. For the clustering part, we will do the same. We'll start by a toy example, and then we'll see on a real data set what we can do. All that I will show you will use TTK, and so please have a look at the TTK website, which provides a lot of state file for ParaView, which can help you reproduce all that we will see today. So first, I will show you a first example that we have here. So what are the datasets that we will be able to use for all the features that I will show you today? These will be datasets when we have a valid neighborhood. So this is what we name a topological space. And we need, on this kind of datasets, to have a scalar fields, which can be, I don't know, the pressure, the temperature. It will be a one-dimensional number that will be attached to each point of your datasets. So here, this is a toy example when we have a 2D dataset with scalar fields, which will simply be the elevation. So we can sweep the scalar of the data just by sweeping along the z-axis, and we will use this to try to understand the features of our datasets. And here, what we will name a features is an area which will be attached to a local maximum or a local minimum. So let's do a sweep in this dataset, and we will try to track what happens as we encounter new parts of this dataset. As we are starting from the maximum scalar value and go to the minimum scalar value, at first, nothing happens until the scalar value we are sweeping reaches the first maximum point of our datasets. Here it's the global maximum, and as we sweep through lower and lower scalar value, we see that we have a region here that grows, and this region, we will track its growth by here marking a point corresponding to the creation of the connected components and making this region growth as we sweep through the dataset. As the sweep continues, we will reach new local maxima of the data, leading to new features. So each feature being kind of a hill here because we are using an elevation scalar field, and we can continue to track the creation of these features here with the corresponding points on the right window. If we continue to sweep a bit more, there is an interesting event here that occurs as several hills merge together in a saddle point. So here after these saddle points, we have a single connected component for the two hills here, so we can consider that we have a single features remaining. One of the two features disappear. Which one we will choose to be the one that remains? For this, we use the elder rules. These rules stipulate that we consider that the youngest feature will merge into the oldest one. So here, if we look at the right window, we have a feature that have appeared soon during the sweep, and a second one that appeared later. And so we consider that this second one is the one that stopped existing here. For now, please don't pay attention to the diagonal. I will explain why it is here after. As we continue to sweep through our data to track the features, a second event of the same type will occur here when we have a second saddle points, and so the new features here merge into the first one that we already had. Same rules, we consider that the largest one continue to exist. And as the sweep continue, there is a last special event when we reach the global minimum of the dataset and the last feature stop existing. And what you have on the right here is a part of the persistence diagram when we have tracked the features that are attached to the maximum, the different maximum on our datasets. Why do we show the diagonal here? This is because when you read the persistence diagram, you can consider that on the x-axis and on the y-axis you have the scalar value that range from the minimum to the maximum, and each bar here corresponds to one feature in the datasets. The lower point of this bar corresponds to the scalar value when these features appear, and the upper point corresponds to the scalar value where this feature disappear. And so the diagonal corresponds to the 1,1 scalar value, if I can say so, and it's just a support for the bars of the scalar values of the features. But here we have only tracked the features that are attached to maxima. We can also consider that they are features attached to minima if we put the dataset in the other side. So let's try to do the sweep on this side from the minimum scalar value to the maximum scalar value. It will be a really similar operation, and as we operate the sweep, we will have new component that appears as we touched the different minima of the datasets, and the corresponding features will merge as we encounter saddle points in the datasets. And in the global maximum this time, we have the persistence diagram which is full. And there we have the feature attached to the minima. And if we make the sum of these two persistence diagrams, we obtain here on the right the final persistence diagram with all the features of our datasets which are topologically tracked through this persistence diagram. Okay, so now let's try to operate the same persistence diagram, but this time, instead of using a scalar field, which will be the elevation, we'll have kind of the same scalar fields, but on flat datasets. So here, we have a flat dataset, but each point have the same scalar value as in the previous one. As I told you in the beginning, the sweep that we operate to compute the persistence diagram is by scalar value. And just it happens that previously it corresponds to the elevation, but it's not the case anymore. So what would be here the result of a persistence diagram on this dataset? I need to select the right field. It will be the same diagram as previously. Okay, if we compare, we have the same diagram. Of course, because the sweep is by scalar value and not using the geometry of the datasets. So now let's try to open several datasets and see what we can do with several persistence diagrams. Up. I'll open this for one. And as usual, when we work with multiple datasets in ParaView, a good thing is to group them into a multi-block dataset. Oops, sorry. And as we want to see what happens, I will display them with a better view. So here are 4 datasets. Here we have just the color that corresponds to the block ID, but we want instead to have the scalar field value which interests us. And now I will compute the 4 persistence diagrams corresponding to these datasets. Intuitive, with a bit of intuition here, we have 1 hill here, 1 hill here, 2 there, 2 there. So we can try to imagine what the persistence diagram will look like at the end. Certainly 1 bar here and 2 there. Let's try to test that. I want to operate on the Gaussian field. Yeah, that's it. And I will also display them with the layout and a bit of space so we know what happens. And what we see here is that these 2 persistence diagrams are just composed of 1 hill, 1 feature, and these 2 have 2 features, a smaller one and a larger one. So now let's do some kind of clustering using these diagrams. Intuitively, we can already see that the 2 upper ones will be in a single cluster and the 2 lower ones into another cluster because they look similar. So let's see if it's what we will obtain. We want 2 clusters. Okay, I will hide that and that. And now I want to see my diagrams, clusters, so cluster ID. And let's show this with a better view. Okay, we have 2 clusters here. 2 clusters for the 1 cluster in blue for the persistence diagrams with 2 features, and 1 cluster in red for the 2 persistence diagram with a single feature. And these correspond to what we wanted to achieve. Now let's modify a bit this example. One of the interests of this kind of clustering is that all we have seen here does not depend on the position of the features on the dataset. As you have seen here, these 2 features are oriented differently, but still we obtain the right clustering at the end. What happens now if we add a new dataset, a one which is a bit different? It will be this one. And I will oops, sorry. Okay, so sorry, it seems there have been some kind of technical issue. I have relaunched the stream, so it should work now. Okay, I am not sure exactly where the stream have stopped, so I will redo this part of the explanation. The idea is that we will do clustering and 2D datasets, which one that will be a bit different from the others. Okay, so here let me open these datasets. When we work with multiple datasets, it's better to group them. So let's group them into a multi-block datasets and display it with a good layout. Up. And now let's show the scalar values that we are interested in. The different datasets we have are here composed of 1 hill, 1 hill, and for this 2 hills, 2 hills, and 2 hills. But this one, the third one, is a bit special because the hills are close to the border of the dataset, which means that here we'll have some features corresponding to minima that will be tracked into the persistence diagram, where here we have a single minimum. So let's try to see the different persistence diagram that we have on these datasets. Up. And show them with the layouts. Here, the single hills have persistence diagram composed of a single feature. Here, the two hills have persistence diagram with two features, as expected. And here, this one have the two features corresponding to the hills, but also two features here corresponding to the minima, which are here close to these two hills. So this may be a bit different, a bit difficult for the clustering to have the good result. Let's see what we have in this situation, and I will tell you how we can solve the problem. So let's do the clustering. We want two clusters, one cluster for the single features and one cluster for the datasets with two hills. And let's show these diagrams in a nicer way. Stars here. Okay. Up, and we want to show them using the cluster ID. So we have two clusters. Sorry. One cluster here contains the persistence diagram that have features attached to the minima, and the second clusters get everything else, so the single features persistence diagram and the persistence diagram with the two maxima, the two features attached to maxima. This is not what we want at the end, because we are only interested in our datasets in area that are attached to the maxima of the datasets. So we can tell the clustering algorithms to only operate with pairs that correspond to maxima features. And if we do so, this time we obtain the good results, as we have here the clustering with one cluster corresponding to the features attached to the maxima, so the single hills datasets, and we have one cluster here with all the others datasets, so the one where the features attached to the maxima are in a number of 2. Okay, but this is a toy example. Now we'll try to do the same clustering, but using a real-world dataset. So this dataset is composed of images of a hurricane. Oh, sorry. At various time steps. So here again, we want to group this dataset into a multi-block as it is more convenient, and I will display them in a better way so we can see what's inside. So we have 11 time steps in our datasets. The first line at the top corresponds to 4 time steps at the beginning of the simulation. The line of the middle corresponds to 4 time steps which are in the middle of the simulation. And the last line corresponds to the last 4 steps of the simulations. And here, the scalar value is the speed of the wind on each point of the datasets. It's the magnitude of the velocity field to be a bit more accurate. So we will try to compute the persistence diagrams for these different datasets and try to operate a clustering on this to see if we can recover which persistence diagrams is close to which time step. So here we have our persistence diagrams. I will show them next to the dataset, it will be better. Up, 1 second. Here. We can see that just at the naked eyes, we don't really see easily different distinctions between these datasets. But let's see what our clustering algorithms can do with this information. What we want here is 3 clusters, as we want 1 cluster per line at the end. I will show the clustering in a new window. So I will hide it here. Up. And I will show it here. We will still use the star view, which is a better way to understand what's happening here. And we already see that it's not exactly what we expected. Cluster ID, and to have a better identification of which diagram corresponds to which dataset here, I will write the ID of the corresponding diagram next to each persistence diagram. Okay, so what we see here is that we have a first cluster that contains the diagram 0, 1, 2, and 3. So 0, 1, 2, and 3. The first cluster is right and contains the lowest line of our datasets. Then the second cluster only contains two diagrams, the two diagrams that are the two first one of the first line, and unfortunately the last diagram contains everything else. This is wrong. And this is wrong for two reasons. The first one is that it can be a bit intuitive. In a wide scalar field, the features that are the more relevant to study are the ones attached to high velocity area. So as we did for the hills, it's better here to use only the pair attached to the maxima. But it's not enough. It's not enough because here we have a last parameters and the clustering that I didn't speak to, and it's the last one here, the geometrical lifting. As it is parametered here, we only use the geometrical position of the features to determine the clusters. So everything about matching the persistence diagram that are close to each other is not used with these parameters. What we want here is to match the diagrams that are similar in terms of features. So I can here change this parameter continuously to use this matching. And then if I do so, I can see that this time we have the right clustering where each cluster contains 4 persistence diagrams corresponding to one line in the original datasets. And here, to be fair, we can vary a bit this ratio between the geometrical position and the persistence diagram, and it won't change the result that we obtain here. Eventually it can change the cluster ID, but the cluster will stay the same. Be careful though, if you only use the persistence diagram matching, you can still have some troubles, as here for example, we use only persistence diagram matching, and this is a bit too much. So we have wrong clusters at the end. So as usual in this kind of problematics, it's better to use a compromise and to use both the geometrical information and the matching of the persistence diagram to have a good result. All that I have presented here have also been shown in a paper that have been presented in IEEE Vis the last year. So I will refer you to the TTK website to have more information about how the persistence diagram matching is done. It's an association problem to solve. And now we will see together how we can reproduce kind of the same state by using the TTK website state file. So this can be done in a single command. If you have downloaded the right repository in the TTK website, you just have to use ParaView and use the state command and select the persistence diagram clustering state file, which is given with TTK. And now we will have kind of the same version of the clustering that we just saw, but in 3D. Hope. And this is the same dataset, but in 3D this time. And we can see that we have here again the 3 different regions with the beginning of the simulation, the end of the simulation, and the middle of the simulation. And we have the clustering which is done there. So that's all what I had to show you for today. If you have any question, I would be happy to help you in the chat. Otherwise, please have a look at the TTK website and have a look at the TTK data that contain the state that I just showed you. And of course, you can always ask the questions on the discourse of ParaView if you need any help to reproduce these kind of things. I will have a look now if you have any questions. For your information, the next webinar will be given on the subject of LiDAR view, which is a software which is really useful to analyze LiDAR information. So these are the camera that also take the depth of the images. So I will still wait a bit for any questions, as I have a bit of a delay here. So thank you again for having been in this TTK tutorial, and I hope to see you use TTK a lot in the forthcoming events. And thank you very much. Bye.